Alright, welcome back everybody. In this video we're going to talk about what I term an extremely important fact, because this is something that's going to come up over and over again with improper integrals and comparison, and it's also something that we're going to use extensively once we start looking at infinite series, and so it's an extremely important fact that we need to know and understand. If the lower limit of integration a is some value greater than 0, then the integral from a to infinity of 1 over x to the p dx converges for p greater than 1 and diverges for p values less than or equal to 1. And so what this really is saying is that if we have an integrand that goes to 0 fast enough, the integral is going to converge. And we're answering the question now, how fast is fast enough? Based on this, integrands that go to 0 faster than 1 over x converge, and ones that go to 0 more slowly diverge. So let's take a look at why this fact right here is true. We're going to break this down into two cases, and we have to because of the behavior of the integrals being slightly different. We're going to break it down into when p is equal to 0, and when p is equal to 1, let's try that again, and when p does not equal 1. Sorry, I had a little brain part there and said 0 instead of 1. Alright, so let's look at this when p is equal to 1. Then I'm finding the value of the integral from a to infinity of 1 over x dx, which is equal to the limit as b goes to infinity of the integral from a to b of 1 over x dx. And I can find this by using antiderivatives. It's the limit of b goes to infinity, and the antiderivative of 1 over x is the natural log of the absolute value of x. But since a and b are both positive here, I don't need the absolute value. So this is b equal to that, which is the limit as b approaches infinity of natural log of b minus natural log of a. Now since a is a non-zero finite value, this piece of the integral is going to be a non-zero finite value, and so our convergence and divergence entirely depends on the other piece. As b approaches infinity, the natural logarithm of b also approaches infinity, and therefore this integral diverges for p equal to 1. Alright, next let's look at the second case when p doesn't equal 1. And so we're going to take the integral from a to infinity of 1 over x to the p dx, and that's going to be equal to the limit as b goes to infinity of the integral from a to b of 1 over x to the p dx, which is equal to the limit as b goes to infinity of the integral from a to b of x to the negative p dx. Now integrating this, we'll just go ahead and use the power rule. And so we've got x to the negative p plus 1 over negative p plus 1. And so this expression is the limit as b goes to infinity of e to the negative p plus 1 over negative p plus 1 minus a to the negative p plus 1 over negative p plus 1. Again, in this integral, since a is a non-zero finite value, this piece of the integral is going to be a non-zero finite value. And so for determining convergence and divergence, we're focusing on the second portion of this part right here that I'm highlighting right now in green. And two different things happen here, depending on whether p is greater than 1 or p is less than 1. When p is greater than 1, that makes the exponent negative p plus 1 is less than 0 for that, which means that we're going to have an infinite value in the denominator of this expression as b goes to infinity. And therefore, this converges for those values, because this approaches 0 as b approaches infinity, since the exponent brings it down into the denominator, and so we've got something over an infinite amount. Conversely, when p is less than 1, that means that that exponent is positive, and therefore we're raising something going to infinity to a positive power in the numerator of this, and that's going to grow to infinity. And so these values, for these values, it diverges. And that entirely illustrates our case by combining case 1 and case 2. We know that this integral, the integral from a to infinity, of 1 over x to the p dx, diverges for p less than or equal to 1. And from the other case, the other portion of this case, we know that it converges for p greater than 1. And that's why this integral behaves the way that it does. And that's something that's going to be very important for us down the line. Alright, that's the end of this video. Hope you enjoyed it. See you next time, and have a great rest of your day.